So now what I need to do is actually write out that charge flux again using our result for the gradient of the equilibrium distribution. So, I just take the old expression and I plug it back in. I'll leave myself lots of space because it turns out to be a very wide expression. One thing that I'll point out here is that I'm going to immediately throw out the term that only involves the equilibrium distribution, because I know if there's no gradient in any of these fields and there's nothing driving the flow, then there's no way I can end up with a charge flux. So I'm just going to throw away that extra portion right away. If you actually went through and did the integrals, you would find that it turns out to be zero by symmetry later. So if I keep going and expanding that out, so now I'm going to plug in our result for the gradient. All right, so that involved a dFdE d mu d x term, so that was our gradient in the due to the chemical potential, and then plus our the effect of the gradient in temperature as well. So we'll put that inside of a bracket. And there was, I'll point out that I've changed, so I'm primarily interested in charge flow in the x direction driven by gradients in the x direction. So I kind of know that's how it's going to work out. If you were to try and use other directions of the gradient, you would find that they don't lead to any charge transport. Okay, and then I'm going to add the portion that was due to our electric field. So this is just me copying the equation from the other page, but now plugging in all of our various expressions. Last term was supposed to be df dk, but instead I've expanded it out as df dE times dE dk with an h bar that's sitting around. That's so what I'm doing is I'm essentially exploiting the definition of the group velocity and using the chain rule there to simplify things. So that's what allows me to sort of combine everything and multiply it times the VG in the x direction in the front. Now I'm just going to rewrite that out I'm going to separate, so there's really three terms in that summation there. And what I'm going to do is I'm going to separate them out so that the ones that involve the chemical potential and the electric field will be one thing. And then I'm going to separate the other one, the temperature gradient term, out to be a separate thing. You'll see why in a second. Just stay with me here. All right, so if I write that out, it'll have all of the same prefactor. It'll have the two VGs, the tau, and a dFdE, all summed over all of the k's. And then outside of all of that integral stuff is a term that I'll call the electrochemical potential. It's sort of the combined effect of chemical potentials and an electric field. Sometimes it's hard to separate those effects, so people sort of lump them into something called the electrochemical potential. The other term contains the temperature gradient. So I'll just take the portion that was in the integral that had the temperature gradient out and make that a separate thing. And of course, the temperature gradient itself comes outside of that integral because nothing there depends on K, which was the thing you were integrating over. So then what I'll do is I'll highlight these two things that appear in front of the electrochemical potential and the temperature gradient. So the integral that exists in front of the electrochemical potential is called, you'll recognize it. That's actually the electrical conductivity. So it's the thing that's driven by the electrochemical potential. So if I end up with charge transport driven by an electrochemical potential, that's called the electrical conductivity. The portion that is so it is possible to derive charge transport using temperature gradients, and that doesn't have a name, but in physics they assign it there's a matrix, and one of the matrix components is called L12, which is essentially just meant to be a coefficient that describes how much charge transport you get for a given amount of temperature gradient. And yes, if you have a burning curiosity about what the other two matrix components are, L21 and L22, we will meet those shortly. They have to do with driving, instead of driving charge transport, you can drive energy transport of electrons using electrochemical potentials and temperature gradients as well. So we will meet those soon. So what we found was that we can drive charge transport, so charge flux, using either electrochemical potentials or a temperature gradient, and I called the coefficients that sat in front of those L11 and L12. Let's take a moment to explore one possible scenario that is pretty cool. What happens if I apply a temperature gradient? So like I have a material where there's a temperature difference across it, but I don't allow any electronic flow. So I don't have any charge flux. It is possible for me to do that because the net charge flux can be balanced by this other term that involves L11. In fact, if I take that scenario and I take the ratio of the I guess I should really take E times the charge times the electrochemical flux divided by the temperature gradient, then I'll find that that actually yields a value of L1 over L, or L12 divided by L11, which is non-zero. That's called the Seebeck coefficient, and what it is it basically represents how much voltage you get for a given temperature difference at open circuit. And that is actually the entire basis of thermoelectric materials. It's a pretty cool effect. So we'll explore more about that later to figure out if it's actually possible to use this to do energy conversion from temperature to sort of electronic flow. But first we need to expand some of these nasty looking integrals that showed up in L11 and L12.